It's really an honor for me to introduce our first speaker, the keynote speaker today, Peter John Pearce, because I think you'll see, if you don't know this already, that he is somebody who takes theoretical ideas that both very far and also very wide. He is a product designer specializing in what he calls high performance design, which is a strategy where form is an agent for performance, creating structures and products of material efficiency, long life, and enduring appearance. And his work really has, there's a consistency of intent and pursuit and interest that I'm sure you'll see, but it spanned architecture, building system developments, furniture design, educational toys, playground structures, and morphological research, which he undergoes this research in many ways, including photography. He has a Bachelor's of Science degree in product design from the Institute of Design at Illinois Institute of Technology in Chicago. He worked with Charles Eames, developing as a product designer for him numerous of the significant furniture projects that came out of Eames. He was a recipient of the Graham Foundation grant to develop theoretical morphology, and through that wrote the book, a significant book called Structure and Nature as Strategy for Design. In 67 to 68, he worked for Bucky Fuller and working on his book Synergetics, and also co-authored a book with his wife Susan Pearce called Polyhedra Primer, and as well as developed another book from his ideas through teaching called Experiments in Form, a foundation course in three-dimensional design. He's taught at the University of Southern California in 66 to 67, was an associate dean of the design school at California Institute of the Arts, where he did introduce an interdisciplinary design program further on this theme of really seeing how these ideas can apply in many realms. In 72, co-founded Synergetics, where the theoretical work was applied to toys, kites, and playground structures. In the 70s, developed a space framing joining system, which came out of work that he did, an installation at the Brooklyn Children's Museum. Landmark project, which I'm sure you all know, Biosphere 2 in Arizona. And then developed a chair called Cachette, an ergonomic chair that also stacks, which is amazing. And his latest work is an Ecohouse, which is a prototype where he takes these ideas of high-performance design and embodies them in a prototype for a house. So without any further ado, please welcome Peter John Pearce.
Good morning. Thanks, Keena. That was all lies. How's everybody doing? Okay. Are you dreaming about tetrahedra and other forms? Let's see. I'm going to try to cover a lot of history in this presentation to sort of give you a perspective on initially where some of the origins of my approach to design come from, and also how those may have been applied to various projects. So morphology and high performance design from Spitfires to the Pearce Ecohouse. A number of you are old enough to remember the Second World War, and the Spitfire is a reference you'll see in a minute to a famous British fighter plane called the Spitfire. But first, morphology, the simple definition of morphology is the study of shape or the study of form. And I'd like to enhance it a bit, the study of principles governing the shape of things and how the shape of things determine performance. And anyway, it's my view that, there's all kinds of slogans. Bucky's was doing more with less. Mies was less is more, and other people use the term form follows function. I don't really care for any of those. So I came up with my own, which is high performance design is achieved when form is considered an agent of performance. Or to put it another way, how well something works really depends on its shape. That's the primary consideration. High performance design achieves exceptional performance, energy efficiency, material efficiency, long life, and hopefully enduring appearance. We'll talk about that more a little later. And I wanted to, it's interesting. I guess I was born to be a designer. I mean, thought of myself as a designer when I was, I don't know, 4 years old or something. And I was in elementary school during the Second World War and was infatuated with the aircraft, especially the fighter planes. And I used to study them. I used to sort of build models, and I would kind of get down on the floor and look at the shape of them. And I always wondered why they were shaped the way they were. And I was also curious that there were varieties. If you look at the images there, these are some of the more well-known ones. The British Spitfire, of course, the P-51 Mustang, the Corsair, and the P-38 Lightning. Those on your right, which were the American planes, and they're highly diverse in the solutions that they came up with. But they all are manifestations of this notion of form as an agent of performance. And the designers of these aircraft didn't go to design school. They didn't do little sculpture projects. They didn't study form per se or form as an end in itself. But they did have a sense that the thing should look right, that it should be a beautiful object when it was all done. But there was a correlation always between the shape of something and its performance. I mean, that was given. I've often said, I hope there are not too many architects in the audience because I may say offensive things regarding them, but if you hired the typical architect to design an airplane, it would not get off the ground. And it's because shape in conventional architectural approaches is not considered an agent of performance. It's considered a way to sell space in the building, or it's considered a status or an image-making device. It's considered, in some cases, fine art or high art, which is a concept that I basically reject. And you look at the so-called elliptical wings of the Spitfire. That was driven by certain considerations having to do with both aerodynamics and load distribution into the base of the fuselage, et cetera. So this is what I was, during the war when I was in elementary school. As I got a little bit older, I realized that the possibility of learning to fly a plane was fairly remote. That took money, and I lived in a small town in upstate New York, and the only airfield there was grass, and the only planes that ever landed were Piper Cubs. So that was not an option. And as you get older, somebody like me who's kind of a motorhead, you start thinking, well, at least I can learn to drive a car pretty soon. And so my interest tended to drift off to automobiles, and in the late 40s, I became interested in basically European endurance racing cars, and went through the same exercise of really being responsive to the form of these things, the shapes and so forth. And these cars were purpose-built to win Le Mans, basically, 24-hour race. But if you look, the C-type Jaguar at the top there won Le Mans in 1951 and in 53, and it was designed actually by a guy named Malcolm Sayer, who was an aerodynamicist that Jaguar hired to do this. And you'll notice the cutaway view, which shows a space truss, and that was the first time I ever saw or thought about triangulated structures. And so it was a minimalist vehicle. It also had some very cool seats in it, which I noticed, and I didn't know at that time that I would end up being a seating designer, but And then, of course, the lower picture there, the 300 SL chassis is also, that was early 50s. Was a very, they were using the triangulated frames for, obviously, for very high strength to weight solutions, because the goal here was minimum drag, minimum weight, which gave rise to the best power to weight ratio relative to the available engines. And then the D-type Jaguar, which is also designed by Malcolm Sayer of Jaguar, was really built like an airplane. It's all riveted together. It was the center of it is a monocoque structure similar to the way an airplane is built. And the Porsche was designed by Erwin Commenda, that was 56, somewhere in there, which also had a triangulated space truss chassis with this minimalist low-drag aluminum body wrapped around it. And I always thought these things were absolutely beautiful. I still do, but they weren't driven by that. They were driven by these other performance issues. I then realized that when I was in college at the Institute of Design in Chicago, that because I thought I wanted to be an automotive designer, that I thought that Porsche didn't need me, and I was terrible with languages anyway, and Detroit wouldn't want me. So I thought I better figure out some other interest here. And by pure chance, we went to a field trip to the Merchandise Mart in Chicago, and we went into the Herman Miller showroom and the Knoll showroom and saw these incredible modernist seating devices, and I just thought, wow, this is incredible. And I think these were the beginnings of ergonomic thinking and seating design, where the chair was minimized and directed directly towards supporting the human body, the anatomy of the body. So the shapes, and these shapes are not arbitrary shapes. People talk about modernist 50s furniture design as a style, but it was not a style at all. It didn't come out of that kind of consideration. I decided that the only place I could work, because I didn't want to be a style, I was, quote, an industrial design major, what we called product design. Didn't want to be a stylist. I didn't think that was meaningful. And so I was able to get a job, my first job, with the Eames office, and worked on these various projects. And I'm going to disrupt the continuity of this chronology here. And what happened is that I sort of met Conrad Wachsman, I'll come back to that in a minute, and then later learned about Bucky when I was at the Eames office. And of course there was, we'll get to that in a minute. So skipping ahead, I spent many years after the Eames office, both teaching and developing some more, working on morphology and so on. And we'll come through that. But skipping ahead, this was the chair that I designed around 1996 and sold to Steelcase. And it's just another example of how form becomes an agent of performance. This is the desk version, which reclines, and it's made out of injection molded polypropylene and injection molded nylon, glass-filled nylon. There's no metal on the structure at all. It's 100% recyclable. And then this is the stacking version, and when you try to stack a chair, it constrains some of the shapes, so that was a consideration. But one of the questions that you always end up with is, if you have an idea for something, in this case a mechanism, that would enable this reclining, the idea of the chair was that you could, first of all, if you're going to design an ergonomic chair, it's axiomatic that it has to have motion. You can't have an ergonomic chair if it doesn't move in some way. And so the concern would be to have a recline capability that didn't require a tension adjustment, so that it was so that any person of any size, weight, whatever, could sit in it without having to adjust the tension. So that required a certain concept of what I call a balanced action. And so you have this idea, and you make some sketches, and later some computer drawings, but then you say, how do I validate this? How do I fine tune this? And as a student of the suspension of racing cars, I knew something about how you can change the dynamic behavior of a structure. So I built this prototype, which is all aluminum, but which was fully, I could change all the linkage lengths and change the spring rates, and the aluminum chair is actually more comfortable than the final production chair, even though, as my daughter said, it looks like an electric chair or something. But I took that chair to Steelcase, and they basically bought it on the spot, and then I spent the next 3 years working with them to put it into production. But again, it's all about form as an agent of performance. Chairs in production has been selling very well, which has been very helpful, to put it mildly. The next group of influences, when I arrived at Illinois Tech, it was the fall of 1955, which was the very day that Crown Hall opened. And Crown Hall is the famous and great classic Mies van der Rohe building. And that was kind of a revelation. I had spent my first year at Syracuse, which is kind of an Ivy League looking, old buildings with ivy all over them, literally, which was quite beautiful, but it didn't seem, and it was a football-oriented school. I couldn't care less about football. And I thought, wow, I went to IIT, and it's in the near south side of Chicago. I said, wow, this is really some serious stuff here. I kind of like the feel of this. I wasn't interested in building an architecture because I didn't think I was smart enough to deal with it. It just seemed opaque and unintelligible. But I kind of liked the Mies buildings initially until I understood a little bit more about them. But one of the great things about this building was it was a huge, open, clear span space. And what that did is, with glass all around, so you had tons of daylight, which I found, contributed to my sense of well-being, although the Institute of Design was in the basement. There was a kind of upstairs, downstairs aspect to that. That's a whole other story we could talk about later. But anyway, it was the first time I had any awareness of this notion of a big space that was then totally flexible within it, so that you could rework the plan and the functions and so forth. And that was pretty cool. And then when I went to work for the Eames office, there was, of course, the famous Eames house, which I saw very, very often during that period. And that was kind of a little bit beyond the Miesian thing, because it was really a kit of parts kind of structure made out of components that you could identify. The Mies approach became a style, because you really couldn't quite see how it was built, even though that was the illusion. While I was at the Eames office, I met Conrad Wachsmann. Does anybody know who that is? Yay. That's a scandal that you don't know who Conrad Wachsmann is. Joe, you don't know who Conrad? Yeah, you must know. Raise your hand if you know. Conrad came to the U.S. Around 1940 with Gropius, or Gropius brought him here, and he, among other things, he designed Einstein's house in Austria, and he was a builder of wooden structures. But he wrote a book called The Turning Point of Building, which was published in English around 1959 or 60, which I stumbled across. And the picture there is a airplane hangar he designed for the Air Force. Never got built, but he was at the Institute of Design when he did that, but not when I was there. He was there before that. But he was talking about industrialized building, prefabrication, componentized building, and this kind of thing. And you should look up the book. It's called The Turning Point of Building. It's got to be in the library somewhere around here. It's it's not printed right now. But and then from Conrad I got to Bucky, because Bucky was in the book, in Conrad's book, and I was very taken by Bucky, and particularly when I looked at the Robert Marx book, which was, what was that called? The Dymaxion World of Buckminster Fuller, I think. And then there was another book that Braziller published by John McHale. And the jargon I didn't respond particularly to the jargon. I mean, it seemed like a smokescreen to me. But the structures really made sense to me because they were coherent. You could look at a geodesic dome made out of struts and you could see how it was built. It was understandable. And to me, building was a mystery up to that point. I could, wood balloon frame buildings, I still find incoherent. I can't, they're fraudulent because you don't understand how they're built when you look at them. They're just, you put up studs, cover them with drywall, which is mostly dog shit, I mean, it's a horrible material. You try to hang a picture on it and the whole wall falls down, and so forth. So that was very important. I didn't understand the geometry. I didn't know what the hell he was talking about half the time. The next influence was when I started teaching at USC, which was in early 60s. When I was working at my Grant Foundation, was a guy named Ralph Knowles, who you probably never heard of, who has written a couple of books. One is called Energy and Form. This is circa 1978, in which he talks about, he doesn't use the jargon that I use particularly, but the form as an agent of performance with respect to how you manage sunlight and the impact of sun radiant energy on building form. And the images there are very large hypothetical buildings that are a direct diagram of the Earth-Sun geometry through the seasons. It's an average of all the sun angles, presumably in this case at Southern California latitude. And he also had an analysis of indigenous building and how the Southwest Native Americans responded with virtually no resources to the management of climate. And the Mesa Verde Pueblo, you can hardly see that image, but is a brilliant example of that, where they said, oh, let's build in that cave because it's oriented to the south, and in the summer I'll be in the shade, and in the winter I'll be fully in sun, and that way I'll have some cooling in the summer and warmth in the winter, thanks to solar radiation, basically, or the absence of it. So that was a very important, excuse me, idea, and I didn't fully appreciate it at first. And Ralph Knowles had done a lot of studies, and he's done other books on regional planning and so forth. The other influence that was very important to me was the Crystal Palace built in 1851 in London, and it was the first World's Fair, World Trade Show, if you will. What's kind of fun for me is I happen to be a saxophone player, and that was the first time Adolph Sax exhibited publicly his array of saxophones. Anyway, I call that architecture as product design. Well, these were all cast iron components, standardized components that fit together to make this incredible structure. Still, probably still my favorite building in history. And what always puzzled me is there was this great statement in 1851, and somehow the lessons of that statement were totally lost in the training and perceptions and visions of architects. I mean, I just don't know. It wasn't until, the 30s, the Bauhaus, especially Conrad Wachsmann, who was not even part of the Bauhaus, Gropius to some extent, started to pay attention to that, and then later, of course, the British high-tech guys, Norman Foster and I'm having brain fade. Alexander Graham Bell was another one, and he was also in both the Crystal Palace and Bell were in the Conrad Wachsmann book, and Bell really built the first so-called octet truss, or I don't like to use these Bucky terms, isotropic vector matrix, or whatever you want to call it, equilateral three-dimensional space truss, both for land-based structures. He built a large observation platform on his Nova Scotia estate, but he built these crazy, wild, big-ass kites out of these arrays of tetrahedra. And there's a wonderful essay in a 1903 National Geographic where he explains his interest in this particular geometry, which I recommend. And of course, Bucky was, I was totally enamored with Bucky in the 60s for a while, worked with him for a year, as was mentioned. But I think the one thing that bothers me is that I think his most important contribution to building has been largely overlooked and never talked about, which is that there are two really important things that were demonstrated by all these domes that Bucky built: the large domes, small domes, aluminum domes, steel domes, cardboard domes, fiberglass domes. The first thing was that these structural principles are scale independent. A triangle is stable whether it's a small triangle or a big triangle. It's a really important idea. And the other is that they're material independent. A triangle works if it's made out of aluminum or steel. And you came out of this background of, which was kind of almost a Bauhausian notion of truth to materials, which I think this basically rejects. It says that truth to materials is important, but it's a lower order idea. And when you design, so at the bottom I say strength of geometry, which is what I like to call it, is that is the shape. If you're designing a structure, a building, or whatever, the first thing you want to do is get the shape right. If you're trying to manage the distribution of the resistance to force and so forth. And then you worry about strength of materials. In normal, when you go to architecture school and you take engineering, what you take is strength of materials. And the tacit assumption is that building form is already known, which is usually orthogonal, right? I mean, so you learn how big to make the beams to resist the moment loads on the joints because there's no triangulation. That's changing now, but so strength of materials is extremely important, but it's not the primary, should not be the primary design determinant of structure. And one of the problems in architecture is, in this country especially, you have kind of a class, an upstairs, downstairs kind of culture. You have the architect who's the Christ figure, and then you have the engineer who's kind of the Antichrist. He's the engineers historically are not given permission to contribute to the form of a building. Their role is to validate whatever the architect wants to create. I mean, that's kind of thing. So this is a very radical and important idea. And and it's not that it's a dome. The fact that it's a dome is almost irrelevant as far as I'm concerned. I mean, the dome is a good structural shape, but there are a lot of good structural shapes, and there's nothing sacred about it. It's the idea that it can be small and big and different materials and so forth. That is a much more profound idea than spherical icosahedrons. Okay, nature's form is determined by intrinsic first principles that govern the shape of things. In nature, all form can be considered a diagram of forces. Can you hear me all right when I wander around a little bit off this mic? I can't. I have no idea from up here. Diagram of forces in which patterns of least energy prevail. In other words, patterns in nature are always the most economical pattern given the set of circumstances under which they occur. And this concept of form as a diagram of forces comes from Darcy Thompson, a book called Growth and Form, which is written in the early 20th century, which is, I recommend, which is a book on the formative processes that determine biological form. And it's one of the most wonderful books I've ever read. I mean, it's just a beautiful, wonderful book. So, by implication, natural structures embody the first principles of high-performance design. So, one says, okay, if you're trying to come up with a strategy, a philosophy, an attitude, an understanding, and some insights on how to deal with high-performance design, maybe we should look at nature. Well, in fact, that's the only source we have, right? I mean, there is no other. Nature is it. I mean, you can't. So what the RISD folks are doing is a very important, I mean, this nature lab is a phenomenal thing, and I don't know what its origins are, but I suspect originally it was the freehand drawing class would go in and draw the shells and the seeds and whatever, and which was kind of the cosmetic aspect of nature, which we all love and enjoy, but there's a deeper issue there, which is more profound, and in which the outward appearance is a byproduct of. So, one of the concepts that I harbored early on when I was doing my morphological research, because I was doing morphological research not because I was interested in morphology per se, but because I was trying to find a better way to build things, architectural scale structures. And I felt that there was not a good theoretical underpinning for this, and I thought that Bucky maybe created the spark for this, but his ideas were way too limited, and I'll talk about that a little later. But so one of the concepts I came up with was what I call minimum inventory, maximum diversity systems. And the tacit assumption in that is everything is made out of a kit of parts. There's no such thing as homogeneity, that you have, whether you go back to the chemical elements or wherever you want to start, at whatever level of scale you want to start, that at some point everything is made out of a set of components. And I like to use the snow crystal as an example of that, because as far as we know, no two snow crystals are alike, yet they all have hexagonal symmetry. And you have a phenomenon of, referencing back to this notion of form as a diagram of forces, you have intrinsic forces within the system, which would be the water molecule, right, and its rules, which are not really rules, they're physical constraints, physical interactions. And you have the extrinsic forces, which is in this case the environment. So you have a snow crystal typically grows around a particle of dust somewhere and starts to grow, and the final shape is determined by atmospheric pressure, temperature, wind velocity, humidity, and so forth. No two snowflakes can be, well, there's what I call Pearce's law of spatial exclusion. Two things can't occupy the same space at the same time. So it's axiomatic that you can't have two snow crystals forming at exactly the same time and place, right? So it follows from that there's going to be infinite variety. The variations can be very small, but it's a comment on the adaptive quality of the water molecule. In other words, it's responsive, and of course, it's a scalar thing. We're looking at you can see a snow crystal like this without a microscope. I mean, sometimes, if you have good eyes or some, 2.75 lenses on your glasses. But the kit of parts is so tiny, I don't know what the scale relationship is, but it's incredibly small. So this is in terms of how many, if this was a structure that we're going to build, in terms of how many struts it took to build that snow crystal, struts as in three-dimensional trusses, it probably would take billions of struts or atoms or whatever. So that's an important thing to understand, but it's the idea. So here's more examples of the snow crystal. Pretty amazing stuff. Another example of form as a diagram of forces, of form as an agent of performance. The water, again, the water molecule, the water is changing elevation. I guess we can't say downhill, but that's what we mean. And it's flowing through a terrain, and the terrain is dictating the interaction of those forces produces the path of least resistance for the river meander. It's just the most economical solution. The same thing with erosion patterns. You have here, Bryce Canyon in Colorado, and on your right is just some beach erosion. The soap bubble becomes a kind of quintessential demonstration of cellular phenomenon. If you build a single bubble, it's of course spherical, but if you want a coalesce bubble, they become polyhedrons, right? But they become polyhedrons. They look random, and they're random because they're not all of equal volume, right? And but they're extremely ordered, and they're ordered by virtue of at every vertex you have 4 members meeting at the tetrahedral angle of 109 degrees 28 minutes, and without exception. And you'll notice that the edges of the polyhedrons are slightly curved in many instances, and those are tangent curves at that 128 degree, 109 degree 28 minute angle. This is the famous tetrahedral angle. If you join this, and the drawing is just the cross section, which shows that the planes, the surfaces are meeting at 120 degree angles. It's absolutely, and you can blow soap bubble frost until you're blind, and you'll never find an exception to that. It's also true of all other cellular phenomena. Next time you have a beer, or wash the dishes. There's a lot of guys in here, they probably don't know about washing dishes, but maybe that's changed in the modern world. But so you can look at a lot of the B cell is a kind of a limited version of that same idea, where you are storing the greatest amount of honey with the least amount of beeswax. Extraordinarily uniform, and that's because the bees are all the same diameter when they build this thing. And what I was going to say about the soap bubble, if you go to the center of each adjacent bubble and join them with a linear member, you'll get a fully triangulated truss system. It's the dual net, if you will. If you have a set of random dots and you want to build, let's say those are cities, and you want to build the most economical road network to join them, it would be that pattern with the 120 degree angle. If you closest pack circles as opposed to a square grid circle, if that's your orchard and you want to get maximum yield, you'll get about 10% more yield if you closest pack them and so forth. The leaf patterns, again, there's some nuances. The cracked mud on the lower right, the 3-rayed intersection is the pervasive pattern that you see. In the case of cracked mud, it's just a probability issue. The idea that you could have 4 members meeting, 4 cracks meeting at one point is extremely unlikely. Basalt columns, which are rapidly cooled volcanic material, form these hexagonal prisms. These are all patterns of least energy. This is metal structures, the one on the right it's aluminum tin alloy. The tin is the dark and the aluminum is the light, and it's soap bubbles again. The upper left is etched surfaces of aluminum, and those are the different crystals within the array forming those patterns. Here you have coral and pollen. Anybody know what the lower right is? I'm sorry? No, it's a watermelon. It's a section through a watermelon. But that's what Darcy Thompson called the polar furrow, that line segment between the 2 vertices, creating those 120 degree angles. They're very pervasive. That's the kind of the fundamental organizing principle of that. Okay, then we move on to take a quick look at kind of general morphology, which really deals with geometry per se. I'm making the assumption that we got a late start, so I'm going to continue. And everybody knows that these are the Platonic and some of the Archimedean polyhedra on the right, and I deliberately omitted the icosahedral family, and the reason is that I was interested in one of the things that struck me about Bucky was he was obsessed with centrally symmetric structures of finite closed systems, and he got so hung up with the dome that he never really, he never looked at in any great deal other than his so-called isotropic vector matrix. He never really looked at crystallography, repeating systems, infinitely repeating systems, which is the first thing I wanted to look at, because I felt that a dome makes a great large space, but it doesn't really make a very good small space, like a house, for example. Very awkward and limited. So I was interested in what crystallographers call periodic structures, or infinite periodic structures. And so these are space-filling patterns using a combination of Archimedean and Platonic solids, but you'll notice there's no pentagonal dodecahedrons and no icosahedron in there, because why they don't fill space? Because of the high symmetry. So if you start looking at this, you then realize that the minimum definition of the minimum way to describe physically as opposed to mathematically space filling or repeating systems is with networks or frameworks. And you see a packing of truncated octahedra on the upper left, and then on the right is a pentagonal dodecahedron, which turns out there's some ways that you can fill space with combinations of pentagonal dodecahedra if you compromise their symmetry. In other words, those are not perfectly regular dodecahedra. I don't want to spend a lot of time. Then you have open networks. On the left is the diamond molecule, which is a so-called four-connected with this famous tetrahedral angle again. You have some three-connected nets on the left, which these do not form. What the hell did I do? I keep my hand over this. Sorry. They don't form planar-faced polyhedra. They're just open networks, and we'll come back to that in a minute. What I was interested in is kind of developing a coherent way to look at all these relationships as one system, and came up with this concept of which I call the universal node. And this is an updated version that we're working on now. Originally, you'll see in a minute, it was as my injection molder called it, a star-shaped gizmo. It was a node that had 26 spokes. In this case, it's got 26 sockets, and they correspond to the symmetry properties of the directions that are represented. And the reason there's 26 is if you started at the center of a cube, or if you just started with a single node and you went in 6 directions at 90 degrees, you would create the corners of a cubic array, right? It'd all be 90 degrees. If you then go let's say you're at the center of the cube, if you go from the center of the cube to the corners of the cubes, you create a structure that is less familiar, which is a network of 8 connected nodes, which are directed perpendicular to the faces of an octahedron. And then if you go to the center of the edges of the cube, you get the famous isotropic vector matrix again, or the equilateral triangular grid. One of the things that came to annoy me about Bucky's Synergetics, and this is heresy, I know, but I'm going to say it anyway, is this notion that somehow the tetrahedron is the key to the universe, that you can account for all these phenomena by starting with a tetrahedron. And he created this polemic between the tetrahedron and the Cartesian coordinate system. And if you think about the Cartesian coordinate system, it really is tetrahedral, because you can find any point in space with 4 pieces of information: the origin and 3 data points, and those are ultimately the vertices, or at least symbolically the vertices of a tetrahedron. I don't find Cartesian coordinates to be a limitation at all. In fact, we use them all the time, and you can define these directive. You see the tetrahedron, the octahedron, the cube, and then you see at the bottom the tetrahedron within the cube, the reference to abstract points in crystallography. crystallographers use a method they call the 7 crystal classes, which identifies points in a system of points in space based on parallelepipeds. A parallelepiped is a generic hexahedron. It's a cube without 90-degree angles necessarily. The cube being a special case of a parallelepiped. They'll all fill space, and then they locate the points, and then from that they get to something called the Bravais lattices, which there are 14. And then this is all presented nicely in my book, Structure and Nature, and then from the Bravais lattices, they generate what they call 230 space groups, which are all the possible symmetrical arrays of points in space. And they use that as a tool to identify the geometry of different molecules, different crystal arrangements, atoms in space. And I spent some time learning about this because I couldn't read the books that I was trying to read without understanding it. And I thought it was really an interesting concept. The problem with it is that it doesn't address the physical relationships between these points. That is to say, it doesn't connect them. And what I was interested in is, okay, you can have alternative ways to make networks or frameworks or arrangements of struts. What are the physical implications of these alternatives? And so this modeling system came about because I was trying to not make a toy, but make a tool that you could physically represent, if not the 230 space groups, although we could probably do that. I was interested in some more basic stuff. And this just shows some other things you can build with it, the rhombic dodecahedron, and a cube in the rhombic dodecahedron, and so forth. And then the actual node, which is the core of that, is a rhomboid cuboctahedron, which you see in the lower left, which is a truncated cube or a truncated, it's a version, if you start with an octahedron and truncate the vertices and the edges, that's what you'll get. If you start with a cube and truncate the corners and the edges, you'll get that. So that's why it's called a cuboctahedron. It's both a cube and an octahedron. So the triangular faces are parallel to the octahedron. And then, speaking of the cuboctahedron, we have that, and the body-centered vector equilibrium, or cuboctahedron, the Bucky called the vector equilibrium. And then you see the dodecahedron embodied or floating within the. These are computer drawings, by the way. They're not actual physical models. We have done some rapid prototypes of these, but it's much easier to get a nice computer drawing than a photograph of these things. And then this was an earlier version, which was the star-shaped gizmo, same thing. But the idea was that the different directions are symmetry axes. So the so-called cubic-oriented direction was a square branch that fit on a square spoke. The body diagonal was a triangular branch that fit on a triangular spoke, and the face diagonal, which is the isotropic vector matrix, was rectangular. So when you assemble the model, the nodes would always remain parallel. So you didn't need to know anything. If you had a round spoke, you could get disoriented very rapidly unless you knew what you're doing. And it was a very effective tool. These are just more models from that. Boy, this thing is really weird. I just touch it and it changes the slide. I don't know. And you can even get, that's a 50-faced polyhedron, which I think I invented, but it's trivial. At the lower left is a space-filling tetrahedron. And the mythology is you can't fill space with a tetrahedron, but that's not true. It's not equilateral, though. It's got 4 isosceles triangles. Coxeter called that the tetragonal disphenoid. I thought you'd enjoy that. And then these are the networks made, again, with the same kit of parts. And this was what I call the universal network. If you build this, if you extend this, all of these different systems are a subset within this model. And then you can go, and then you can look at these problems with the icosahedral symmetry and how do you make repeating structures. And I'm not going to spend time because I'm taking too much time on this, but these are all capable of infinite periodic packings, but they're not space filling because they have voids. And that's an important distinction. And then this was a kind of an important slide. Early on when I met with Bucky, before I actually worked with him on his book, I got him to look at some slides that this is 1965, and I showed him this. And I thought, if you can have sphere packings and you can have domes, why can't you pack domes? And I figured out a geometry that would enable me, and there's more these are part of that, but I could take simple geodesic domes and make these extended. And he said to me, I didn't know that was possible. And the next time I saw him, he said, well, I have a patent on that. No, he didn't. I'm just kidding. Then I got looking, I was puzzling over these networks that didn't define polyhedra, so I thought, well, I had been studying the work of Felix Candela, who builds the hyperbolic paraboloids, the Mexican architect, and people like Luigi Nervi and some others, and was very interested in the minimal surfaces, and so I said, well, if I can make polyhedrons with these open networks by inventing a new kind of polyhedron called the saddle polyhedron. And my crystallographic friend Paul Schlichter called them Peter Pearce's peculiar puckered polyhedra. But anyway, this is, and what's interesting about this is you can have space-filling polyhedra that have only 3 faces. And of course, if you have flat planes, you can't have less than 4 faces. So that was kind of a fun thing. And these are just examples of that. These are alternative space, and all the networks that define these can be built with that model kit. And then that led to something which technically is called the periodic minimal surface, which starts with a saddle hexagon or quadrilateral and is rotated along each edge 180 degrees, so it has a smooth transition from one polygon to the other and creates these sponges or infinite labyrinths, whatever you want to call them. This particular one maps the diamond molecule. If you climb through this, you're going to be following the pattern of a diamond molecule. This one is basically cubic, and you can also, any surface can be subdivided into triangles, right? So the lower right is an experiment along those lines. What we did is we took the diamond geometry and built a large, this makes a very good shell structure as opposed to a framework. And although we couldn't find any clients to build a large building with precast concrete shells, we were able to do this. So this is the diamond molecule that kids can climb through, and it's made out of polycarbonate, clear polycarbonate. And this was, first one was 1975. And we just, there's a special connection system that we had to develop. And so this becomes product development, which is a whole nother, product development is a problem. I think it helps to have certainly helped me to have a good morphological background, but it isn't a requirement necessarily, except what you learn from morphology is Pearce's law of spatial exclusion. You can't occupy, and you start trying to figure out space filling systems, you're going to go crazy trying to do that until you realize that you can't occupy the same space at the same time with the same object. That's pretty fundamental. And then the biggest one we ever built was in Hakone, Japan. It's called Peter Pearce's Diamond Sculpture. It's a sculpture museum in the mountains of Japan, Hakone Open Air Museum. It's a very serious, sophisticated museum, and they, since it's polycarbonate plastic, it's good for about 15 years. It's outdoors, the UV eventually gets to it, so they keep replacing it, and we just replaced it. And this is a computer model using a program called SolidWorks of the latest one we just built. Fortunately, through all my trials and tribulations, I've managed to save the tooling, because this is some serious. These are injection molded parts, and that's the actual installation that was just finished. This was some early, this goes back to 65, studies in non-orthogonal geometries. The sequence on the left is an 8-story building. I called it my bubble building. The middle upper middle is a diamond structure, basically. Each house is a carbon atom. And the idea was that, it's a 2 or 3 story house. So it's a way of exploring reduced density in terms of land use, but at the same time preserving some autonomy, privacy, visibility, ventilation, access to sunlight, and so forth. It's just very schematic, and the very bottom picture on the left is, in fact, a curved space. That was a 20-story building assumed to have precast concrete shells that were minimal surfaces and so forth. So at some point, because I had to answer, got to the point where people like Arthur Loeb invited me to crystallography meetings to give papers, and artists would invite me to talk and stuff, and I thought, am I a sculptor? Am I a crystallographer? What am I? What am I? Where am I going with this? And I always went back to my origin, which was I'm a humble designer. I make things. I build things that people can use, and so I never really lost sight of the fact that the reason I was doing all the morphological research, and I continue to dabble in that, was building. But the problem, and this would, I worked with Conrad Voxman at USC when he had a thing called the Building Research Institute, and he used to bug me because I made these models out of basswood. By the way, if you ever have seen my book, that's all stuff that's either models or drawings. There's no computers weren't invented, it's all done by hand, so we got to be pretty good at it. But Conrad didn't like he liked what I was doing, he liked the ideas, he didn't like my basswood stick models glued together with model airplane glue because the joint, it wasn't Conrad Voxman was famous for calling attention to the importance of the joint for these complex structures. How do you hold them together? And I kind of just brushed them off because I said, well, I'll get to that when I need to get to it. It's not in the critical path at the moment, and I'm trying to understand other things. So finally I got to it, and I came up with this joint, and the trouble with having the morphological background is I knew what all these geometric options were. So I wasn't satisfied to just build one kind of geometry. I wanted a system that would be flexible enough that I could build anything, any triangulated truss system, whether it's flat or curved or warped or stepped. So I came up with this nodeless joint, and engineers say, well, you can't do that because you got to have a node. You got to have a ball there or something for the forces to go through. And I said, well, what is the function of the node? Because I was trying to define the problem, rather than starting with solving a problem by defining the answer, which is to say, I got to design a new kind of node. That's already the solution, right? So I said, what is the function of the node? Function of the node is to hold struts together. And if I define the problem in that way, I could see that there are other ways without the node to hold struts together. So that came out of this, and there was, of course, there's the technology issues. I thought I was Henry Ford for a minute. I had a factory with 150 employees. We made all this stuff in-house. We made the struts, we did the welding. So this is a flange that's flame cut, welded to the end of the strut with a fillet weld that has an end cap welded on it. And we had these simple fixtures, and we could change the angles, in effect the dihedral angles at the end of the strut, and build anything. You name it. And then and as time passed, we got better at it and faster at it, and understood that there weren't really very many useful options in this vast array of morphological possibilities. There weren't very many that really worked as structures. And of course, this is predicated on a fully triangulated system because these are pin joints or quasi-pin joints. So these are different nodes, and you'll see 14 members meeting. You'll probably wonder what the hell is that, because a isotropic vector matrix has 12 members meeting if you extend it, and that's the space-filling tetrahedron that I mentioned earlier. You don't really need the 14 and so forth, but damn it, what is this? I think I must hit that. Okay, anyway. So I spent 15 years working with this system, and the most famous thing we did was the biosphere. Can we turn the lights down? these are pretty good images, but that helps a little bit. And wow, they're really weird. Look at contrasting. Anyway, the biosphere was a 5-acre footprint. I think it was 7 or 8 million cubic feet of volume. It consisted of 5 structures. There was the long structure at the back was the wilderness biome, which was kind of a stepped pyramid. There were 9 intersecting vaults in the middle of the picture, which was agriculture. And then the crazy building in the front was the habitat, and then there's 2 domes, which are not geodesic domes. Talk about that in a minute. This is detailed. The wilderness biome had rainforest and had a coral reef. Has anybody ever been there to the Pfizer? And a desert at the other end. And the problem with the experiment was, all I did was design and build the structures and invent the airtight glazing system and build it. I had nothing to do with the science or the environmental aspects of it. But the goal of the project was to create a sealed environment and try to establish the conditions under which you could have a CO2 oxygen equilibrium between the plants and the humans, the animals. And that's a long story, which I can talk about informally. I don't want to spend time on it right now. I just want to mention but the lower picture is, the left is what we call the boneyard, which is where there were about 80,000 struts that we made on the whole project. And that was the boneyard. The struts would be delivered in those racks that we designed, and you see them on the right. The dome, if you look at that dome carefully, there's a couple of things about it to note. One is it's not spherical. It's kind of if you put a drop of water on a surface, it's kind of that shape. It's kind of flattened out. And it's also not icosahedral. And it turns out that icosahedron is one of many ways to subdivide the surface of a sphere, or any surface in triangulated arrays. It's not necessarily, it may be optimum in terms of minimizing the difference in member lengths, and it may be optimum in terms of stress distribution, maybe slightly, but it's not optimum from a manufacturing point of view. When you're manufacturing things, what you want to do is minimize complexity, which means minimizing the different number of parts. You want to reduce the number of part types. And you don't do that with icosahedral geometries. That was one issue. So we came up with an alternative way to subdivide, which starts with actually 8 triangles at the top. I'm not going to take time to explain it, but the other thing is, when you have a hemisphere, you have thrust coming under load that coalesces at the boundary, at the base, at the footings, and so you have to resolve a tension load or a thrust outwardly at the base. And what this does is, because of the shape, it's kind of barrel-shaped, the thrust is resolved within the structure. So when it gets to the ground, there's no thrust, or very little. And that's a much easier and cheaper thing to solve, because it's a tension load on the struts, and the struts have huge tension capacity. So that's why we did that. So again, form is as an agent of performance. So a spherical dome is not necessarily the best solution, depending on what you're doing. This is just, wow. This is just some erection sequences. And then these are some other projects we did. Reading horizontally, in this case, American Airlines, 1982. These are early 80s. Early studies in climate management, shade canopies that have certain properties. These are some more radial structures. This is, the one on the left is the Pantheon with the oculus, right? I mean, it's got that hole in the middle. That's a double layer structure, but again, we minimized the number of part types. Another dome. These are 180-foot spans. And then the one on the right is a solar collector at Jeddah, 1981, 2-acre canopy with photovoltaics. It was a very early project we did with Arcos Solar. The British Columbia Pavilion is a 300-foot dead flat clear span from corner to corner. Wow, I did that again, I keep. Fallbrook Mall, that's, a lot of these things that they don't, people take them, develop, when they're in shopping centers, you never know what the hell's gonna happen, and they change owners, and someday it's gone, they just take them down. This is Las Vegas, which was, Pearce Structures basically, which is what this company was from 1980 to 90, it kind of collapsed in 95. I'm not gonna go into the details of that, that was not fun. This is a 4-city block long vault. It's 100 feet wide and spans of, what does it say? 200-foot spans, yeah, along the axis of the dome, of the vault. And this was Navy Pier in Chicago. Those are the last two projects we did. The Winter Garden, it's all glazed. So we didn't start out doing cladding and skinning and glazing, but at the end we were doing all of it. So it was a fun ride, but made me old before my time, I think. Okay, Pearce Ecohouse. Pearce Ecohouse is a prototype of a net zero energy approach to design. Again, it's really a culmination of the 50 years of whatever it is I've been trying to do, high performance design. And so the question is, can I take all of this stuff I've learned as a designer, which is everything from how structures work to how things are made, materials, lots of different things, and use that without arbitrary constraints from cultural biases. Without starting with what is a house supposed to look like, because I don't know what this is going to look like. I don't want to start, because most people design, they start with rooms, or they start with, can we be liberated from the cultural baggage? So that's, and in that respect, I think Bucky's first Dymaxion house is in some ways his most interesting work, because it was the thing on the mast, because it was very ballsy. I mean, if you think about the way people thought about houses in America at that time, and said, what the hell was that? Oh, I see. Why don't we, build a house that looks like this? I mean, that must have just made people crazy. And I think that was an important message of, sort of giving one permission to deviate from the norm, right? So that was very, so building design tends to be driven by appearance, sentimentality, fashion, and status. Designers create external forms and then hope their engineers can make them work. And building form is not fundamentally driven by high performance. There are obviously exceptions to this, but that's it's particularly relevant in housing. First principles. So the question is, what is a dwelling? I mean, what can you say about the function or the purpose or the first principles of a dwelling? What does it need to do? And I've been a student of indigenous building for a while, and you look at that and you get a pretty good sense of it, that the first thing is climate management. Without that, you don't really have a building, right? If you can't keep warm or cool, then you have sculpture, right? Or you have something meaningless. Second thing is spatial differentiation, privacy from public, dark from light, so forth. Efficient use of materials. If you're building, an igloo or a stone structure in southeastern Italy, you don't want to have to go very far to get your materials. And you don't want to use any more than you need to get the job done, because it's a hell of a lot of work. So efficient use of materials. So those are all things that you have in the indigenous building world. But I think those are the fundamentals. And then a sense of well-being, which is important. But you can't get to a sense of well-being if you're freezing to death or if you're living in a 120-degree temperature environment. So those are the basics. So those are the kind of guiding principles. Okay, the first principles of climate management, which was deliberately at the top of that. Without climate management, you have nothing. So the two ideas that drive this exercise: solar radiation is the primary source of heat gain. That's indisputable, right? I mean, nobody can argue with that. Temperature differential is the primary source of air movement, and that's also indisputable. Those are basic laws of the physical world. The attributes of this project, I'll run down them really quickly. Passive climate management, high strength of weight material, minimizing closed surface to contain volume. That speaks to climate management as well as material use, right? I mean, you want to minimize transfer. Airtight building envelope, which is, most buildings are extremely breezy, especially houses. Passive energy sources, photovoltaic, geothermal, whatever. Natural ventilation, very important. I mean, we went through this period where all the buildings are sealed, right? Air conditioning is the most, first of all, buildings use more energy than any other. The construction and maintenance of buildings uses about half the energy. Sorry, I said the building enterprise uses about half the energy in the world in terms of construction and maintenance and so forth. The biggest component of that is air conditioning. And so, and especially in Southern California, the idea of climate management with respect to solar radiation is a big deal. Access to daylight, access to view opportunities, column-free open plan. This goes back to MEIS, integrated product system, prefabricated building components. You can read the rest of it. Non-combustible, long-life components, low maintenance, reusable building components, high recycled content. If you're using steel and aluminum, for example, aluminum extrusions at the very minimum use half recycled every time you make one. And they're 100% recyclable. So is steel. Minimum site intervention, which you'll see in a minute. And this is the basic house, which is a glass envelope hanging under an exoskeleton, which is then populated by a louver scheme, which manages solar radiation. And it's a total clear span inside. There's actually two levels. That's the roof plan. There's only two part types in the structure over the whole thing. There's an integral joint system. It's not the one you saw. I have a new joint. There's only one louver extrusion profile, but there's two, east and west. This is east-west is the horizontal axis. So orientation is extremely important if you're going to deal with solar management. And then this is the basic assembly. Now this is a big we work at home, so this is the home office, a serious home office. So we have residential on the upper level, additional space for offices and work and prototypes. In the lower level, there's a garage. So we have about 5,000 square feet of enclosed here, and the garage is 1,200 square feet. So this is basically the structure. Now you could, sitting on the piles, you could plug that in wherever you need to plug it in. So these are just alternative views as you go through it. And there's a radiant system in the floor, which is both heating and cooling, and it uses geothermal sources for minimizing temperature differential in the tubing. It's always about 65 degrees underground. You don't have to go very far. It doesn't change year-round. So instead of starting with ambient temperature to heat or cool it, you start with 65 degrees instead of 40 and 100. So that's very energy efficient. And there's that's a section on the site. And there you see the section, and there's a whole sort of modular furniture system inside, there's no particle board or laminates or anything that will burn on the end. We're in a fire zone. This is 2,200 feet in the Santa Monica Mountains in the chaparral environment. And this is the metaphor of this solution, which is building your house under a giant oak tree, but in this case, a deciduous oak tree, so that in the winter you get the sun warming up. So what you find is instead of trying to beat off the radiant energy with thick insulated walls and all kinds of other tricks, you intercept it. And if you're in a hot climate and you walk under a tree, you can validate that notion that you can easily demonstrate a 10 to 15 degree temperature drop just by walking under a big tree. It could be 100 degrees out and you can feel fairly comfortable if you just walk under there. And this was the Mesa Verde example. That image doesn't show up, but you can see the summer and winter, the diagram of that cave dwelling. And this shows the geometry of the louvers, showing that the louvers are fixed in this case because it's the latitude that we're in it's a relatively mild climate. So, it gets hot, but it's doesn't get real cold in the wintertime. So, what happens is at the lower sun angle, in the cooler months, you get sun coming in because of the geometry of the louvers. If you were in a northern climate, you'd need to rotate the louvers a little bit to optimize this, which could be done without a lot of hassle, but we have enough things to struggle with on this. And this is a 3D rendering showing the summer at the top and the winter at the bottom. And you see what I call solar leakage in the winter. You have sun coming through to heat it up. And then we have, as I started to say, radiant heating in the floor, radiant heating and cooling, which I don't have any of this. We're still working on the product development aspect of my place is full of 3D prints and mock-ups and things, but it's that's the site. You can see the ocean in the background, and there's the house. Not built, of course, it's a rendering. It's a Google Earth shot. And that's the property. Again, that's a simulation. People come to visit and they say, well, we thought the house was already built. It looks like that on the website. This is a plan. It's 2.5 acres. You can see the property line. And there's the topo. And this is, all these images are one model. It's just rotated and renderings are made from it. And we do everything from that. We can do our structural analysis. There's a wireframe underpinning. That's the site. So the surveyor did the topo, gave us a three-dimensional AutoCAD file, and then this is done we use a lot of different programs to get this done. This is the build sequence. There's absolutely no grading. There's a little bit of a road that comes in there, but it's following the contour. You put the piers in. You build the deck in subsections. You bring a small crane in and lift them onto the piers. That's the primary. This is I didn't explain it. That deck, we have a requirement of providing a 65-foot diameter turnaround for large fire trucks because we're in a fire zone, and we were having trouble finding a spot for that, so we just said we'll just make the deck is made out of the same parts. It's just more of them. And so we started at about 7,000 struts. We're at about 20,000 now to build this whole thing. So that's the deck and the garage and the lower level, and then we add the glazing to the lower level, and then we add the upper deck, and there are these buttresses that hold it up, and then we add the enclosure and then the exoskeleton. Now, it wouldn't actually be built in that sequence. The exoskeleton goes in first because the glazed envelope hangs from it. And then the louvers go in last, and then you have the building. The glazing, the whole thing is glass, A, to keep it simple, and B, to exploit natural light. And of course, it doesn't. And of course, the windows open all the way around and also in the roof, so you can So the louvers heat up in the summer, they create convection currents, and they pull air through it. So it's kind of solar cooled as well. And the floor is cooled off with the radiant cooling, and the convection currents will pick that up and pull it through the house. So it's, and the garage is, that's where the photovoltaics are. There's a room for enough photovoltaics to run the whole thing. We have to be on the grids because you can't get the rebates if you're not on the grid. It's a conspiracy, obviously, from the energy companies, but we wouldn't need to be on the grid. My colleague that did the rendering, the helicopter is a joke, basically. We don't expect, although the fire department down the hill has a helicopter they could drop in. This is, with and without the contour. Susie, what am I forgetting to mention? Anything? The what? Yeah, well, it's coming. This is just a fly around. Unfortunately.
Did you say it's fireproof?
Yeah, it is. It's it's all steel and glass and aluminum. There's no combustible stuff inside or out. No fireplace. Everybody says, "Where's the fireplace?" We don't have one. Oh, here's the stair. This was interesting. We don't want a stairway inside between the two layers. I mean, these are not fundamental to the idea. These are just kind of environmental issues. We didn't want an enclosed stairway because for both acoustical privacy and it takes up a lot of room. A stairway takes up a huge amount of room. So we have the stairway, we have two stairways outboard to get to the lower level. Slides are a little dark in this particular. You can see it on the left. Yeah, you can see the stairways there. Yeah, it's a good view of the photovoltaics. Helicopter coming in, successfully lands. He got his, he picked up the mail and now he's. These are just, see a glimpse of the interior. This is one of the buttresses that holds the top up, and it's the same components, it just, and the louvers. The stairway up to the deck, and lower level looking into the interior. This is kind of a fun shot here, this is looking under the deck towards the lower level. And if you look carefully, you can see a stairway. There's a stairway inside the house. Oh, you'll see that in a minute. I'll wait. Just about there. This is the interior of the upper level, which has permanent bathrooms in the back and 2 bathrooms, and then everything else is movable. These are storage walls that store everything you could imagine, from files to coats, and define the functional rooms, guest room and master bedroom, and so we're just kind of looking at that. And this is still the upper level from.
What's the name of the cat?
Well, we have 5.
Okay.
Henry, Sparky, Annie and Oliver, and we have a new one called Cheetah. They kind of come and go over time. Oliver is 14 years old. So he's,
It's an aged cat.
yeah. This is the lower level. And these are, the configurations are changeable, so they're not, we could, partly we make a configuration that'll get us, the building department has trouble with this because although they're very much supportive, they've told us that this was the best, most interesting project they've ever seen and the best submittal package they'd ever seen. But so we're very happy about that. But we're so disparate with the rules of the game that we have a lot of hoops to jump over to accommodate. We got through. What am I doing? Oh, here we go. We're almost done. This is just kind of a walkthrough to give you a feel for what's going on there. Note the Eames furniture and the cachet chairs in there. So the furniture system is also a product. I mean, that's a developmental thing that we're also working on, a new chair. Yeah, here, that's Henry. That's Susie, and that's my daughter, Alita, who works for me. These are elevations, sections.
How will it handle an earthquake?
It'll be impervious to any foreseeable earthquake. I mean, that's just a given. It's mostly on bedrock, but the structure is not going to be. We built 80, when I had Pearce Structures, we built 80 projects all over the place, and when you do the structural analysis for those, you always have to do, this is the site, and that's the view from the site. Palos Verdes and Catalina in the background. What was the question? Oh, yeah. Yeah, we can have questions now if there's time. I finished. We did about 80 projects, and you do the structural analysis, you've got all the load combinations, and which would include seismic, earthquake. Well, lateral is seismic and wind lateral, and the jargon of the engineer is what is the governing load case? In other words, what is the worst case? And seismic on these structures was never the worst case. It was always wind uplift. So seismic is, in these triangulated structures, if they're shaped correctly, right? If you manage the distribution of loads through strength of geometry, they're really impervious to earthquakes. I mean, you have trouble maybe at the footing where it's hooked on or whatever. The governing load was always uplift, wind uplift, and in the case of the Saudi Arabia project, it was 2 acres, we had to put ballast under the ground where the footings were, and the worst case load was a tension load, trying to suck those footings out of the ground. And that is very common. Other kinds of load cases in the north would be unsymmetrical loading, where you have snow drifting, stuff like that. The problem with, the reason I don't do tensegrity, for example, or even any kind of tension structures, the problem with tension structures is you can optimize them for one direction of load, but as soon as you try to cover all the load cases, they get so compromised that they weigh more than just a simple strut, because the strut can work in tension and compression, right? And the cable can only work in tension, so you have this kind of weird phenomenon. So this, if your concern is aesthetics, you want to minimize the physical mass, but it's still a dangerous, treacherous area to go into, because you got to really know what you're doing. You can make some terrible errors, which have been done. Any other questions?
After your house is all done, do you have any dream projects that you've been waiting all your life to finally get to?
No, the house is that project. I guess, yeah.
Let's, maybe if there's one more question we can take, and then there's informal questions we can do outside, because for time. Here.
The, all right. Again, the deck, was that a major problem to get through the building department? Because you mentioned that the fire system would want to be able to turn around or have some access into there. Right. Yet it's above ground, and from the photographs that you showed at the very end of the terrain, there's quite a bit of underbrush and shrub and landscaping that will be a fire condition, and they're above it.
Yeah, well, there's a couple answers. One is that the first answer is we haven't gotten approval yet. Second, although we have interacted with, we're in communication with them. They approved the concept that they could turn the truck around on that platform. They actually liked it because it's fireproof. The second thing is that the landscaping will address things like underbrush. There will not be stuff growing under there that is flammable. So that's really not a problem. They have very strict rules where we live about what kind of plants you can, the proximity to the actual structures, what kind of plants they are, and the whole landscaping is native plants that are already there. We're not bringing anything in other than some possible Mediterranean ice plant type, drought tolerant things like ice plant that are highly fire resistant. But other than that, there won't be any. I mean, the natives are flammable, but they don't require any water, or and they're beautiful. But it has to do with the proximity. By the way, the house will have a outboard sprinkler system within the exoskeleton that will be used for both fire protection and cleaning. You just turn it on once a month and wash it down.
Okay, I think we can continue informal questions. We're going to take a break for about 10 minutes. Thank you very much.
Thank you. I apologize for taking so long.